Okay, so we're going to look at the end behavior of functions today. You should have this paper. You picked it up on the way in. End behavior is a little bit... End behavior can be a little bit confusing when you are switching between talking about increasing and decreasing intervals to talking about end behavior. So we talked about increasing and decreasing intervals last time, and you did the little activity with the cards. So today we're talking about end behavior. For end behavior, we don't care what's happening with the function in the middle. We care what's happening with the function way out at the ends when it's approaching positive and negative infinity. So as we're talking about this, the first column here as x approaches negative infinity. So we're going to look on the left first. Again, I'm going to keep telling you this. As mathematicians, we don't like to write a lot of words. Where the word approaches, that's what you say when you write this arrow. So in your writing this as a mathematical sentence, you won't write the word approaches. So the way this is written usually as x approaches, and we're going to do negative infinity first, f of x approaches, and then we're going to fill in the blank and see what each thing would be. So this is the way it's normally written as a mathematical sentence rather than with all these words. But this is when we're first talking about it. So you need to understand that we're talking about when it approaches. Now, if we're looking at these graphs, I need a better. Highlighter. Okay. As x is getting more and more and more negative, we don't care what's happening in the middle. We don't care about the x-intercepts for this. We don't care about what's happening around the origin. We care about what's happening way out to the left when x is getting more and more and more negative. So last class when we looked at increasing and decreasing intervals, we started at the far left and we looked at what the function was doing from left to right. For end behavior, we don't go left to right. We look way out on the left and see what's happening way out there. And then we jump over and we look way out on the right to see what's happening over there. And we don't care about what's happening in the middle. Okay? So if I think about this function, I know that this cubic function is going down forever, but it's also going to the left forever. Right? There's no asymptote that's going to stop it. There's no boundary. So even though it seems rather skinny, even as it's going down this way, it's still moving to the left. So if I pick a number way out near negative infinity, negative 10 quadrillion or something, where is the function going? Where is it heading? Negative infinity. It's approaching negative infinity. So as x approaches negative infinity, f of x is approaching negative infinity. So then if I look way out over here to the right, looking way out to the right for as far as I can go, as far as I can imagine, towards infinity, what is this function doing? It's approaching infinity because it's going up forever in terms of the function. So this is approaching. Now, we don't normally write the positives, but since we're looking at this for the first time, I will. But normally you don't have to put the plus sign in front of positive infinity. You just need the negative in front of negative infinity. All right, so then if I switch this graph around, what is this minus sign right here in the front? What is this minus sign going to do? Reflect across what? The x-axis. So this that's down here is now going to be up there, and this one that's up there is now going to be down here. These are not accurate drawings, but it gives you an idea. So the green one has been reflected across the x-axis. Right? Now, as x is getting more and more and more negative, what is the function doing? It's approaching what? Positive infinity. Because as x is getting more negative, the function is getting more positive. And then on the right side, as x is approaching positive infinity, the function is doing what? Negative. Approaching negative infinity. Okay. So now I'm going to do, lines are not very straight. It would help if I laid this down. Didn't try to hold it. There, that's better. So this time I'm graphing x to the fourth. X to the fourth looks very much like x squared, except it gets really, really flat around the origin. So it's not quite as pointed of U shape as a parabola would be, because we're talking about x to the fourth. So looking to the left first, because that's our first column, as x is approaching negative infinity, this function is approaching what? Positive infinity, because it's going up on the left, higher and higher and higher. As I look on the right side, as x is getting larger and larger and larger, we're going towards positive infinity. What direction or what is f of x approaching? Positive infinity. Again, we're going to reflect that. For number 4, we've put the negative sign in front, so it's the same sort of function, but it's going this way. Still kind of flat right there on the end. It's not exactly horizontal, it's just flatter. And I didn't draw a good reflection, but you get the idea. So on the left, for this one, as x approaches negative infinity, the function is approaching what? Positive. On this side? Negative infinity, yes. Thank you. And on the right, as x is approaching positive infinity, what's the function doing? Approaching negative infinity, because it continues to go down on both sides. Any questions so far? Most of the time, if we're just looking at end behavior, you seem to understand and you get it. And if we're just looking at increasing and decreasing, you seem to understand it and get it. It's when you have to do both on the same day, like you would on a test, that it tends to confuse you. So just make whatever notes you need to help you remember that end behavior only cares about the end behavior, way out at the ends of this graph, wherever infinity is. What is the graph doing? Anybody not have these? Anybody still copying? Yeah, okay. So do that quickly before I clear the screen to move it up. You have your syllabus with your 3 passes on the back. Fill that in and bring it to me, and I'll sign it and give you the other pass, and you may go. Okay, so everybody's finished copying now. It's okay for me to clear this. Oh, I shouldn't have let that run, but oh well. I'm going to skip over x to the 6th because you can do that one yourself. I want to look at x to the 5th. Put it back over this way so I have room to draw. I want it to go over here. That'll be all right. Okay, so we're going to look at x to the 5th. So does it bother you that I'm drawing in that spot where it's shiny? All right, x to the 5th is very much like x to the 3rd. It's just somewhat wider, and then it does the same thing where it does that flattening out a little bit more so than the cubic does. So it sort of flattens out more and then heads this way. All right, as x approaches the far left, negative infinity, what is this function approaching? On the left. Yes, sorry, on the left. And then on the right, as x is approaching positive infinity, I think I said it backwards the first time. As x is approaching positive infinity, what is the function doing? Positive infinity. Now, again, we're going to reflect this across the x-axis. Right? So we've reflected it here across the x-axis. So this time, on the far left, as x approaches negative infinity, what is the function doing? Approaching what? Positive infinity. Because it's going up on the left. Right? Here, this one. Colors are much prettier on my iPad than they are up there. I don't know why. So on the right side, as x approaches positive infinity, what is negative infinity? All right. So now you're going to turn this over on the back, and you're going to make a conjecture based on what you just saw. And if you need to draw the x to the 6th, you can do that. It's going to look like x to the 4th, only it's going to be wider. But you're going to make a conjecture about when the leading coefficient is positive and x is even, or the leading coefficient is negative and n is even, or if n is odd and the leading coefficient is positive or negative. Right. Anybody not finished with this screen? So I can clear that off. Yes? They look the same except the little flat part is just wider. Yes. So, number 9. What do you think is going to happen when the n, the exponent, is odd and it's positive for the leading coefficient? What do you think is going to happen when n is odd but it's negative? Then when n is even and it's positive, and when is even and it's negative. Put what you think the approaches is going to be, and then without using a calculator, draw the two things for 13 and 14 and check out your conjecture. Is it resuming or not? So what I want to talk about briefly here is just to remind you, do you remember the terminology local minima, local maxima? Yes. Also called local extrema?
No, I don't know that one.
Okay. Local extrema is a general term that means either a maximum or a minimum.
Oh, okay.
And then maxima is plural. If you only have one, it's a maximum. But if you have more than one, it's maxima, plural. And minimum is when there's just one. And minima, oops, I didn't do that right. Minima, that's when they're plural. So I have two local minimums here and here.
And you have one local maximum.
And I have one local maximum, yes. One local maximum here. Now, on the calculator, do you remember how to use the calculator to find these?
Yeah.
Second trace. And then I think minimum is 3 and maximum is 4. I think. Yes, minimum is 3 and maximum is 4. All right. So if I'm just going to guess these approximate locations, in fact, I'm going to erase that highlighting so we can see it a little better. I'm not going to use the calculator. We're just going to guess. This one's pretty close. It looks like at -1, -7, we have a local minimum. And just abbreviate it. And guessing on this one, not quite to 1, so I don't know, 0.8 and a little below 5, about 0.8 and about -5.3. So this is also a local minimum. So we have 2 local minima. And normally you just list them and you put a comma between them. Now, one of these is, in this particular graph, one of these is the absolute minimum. It is the lowest one of all of them, right? So which one is that one?
-1, -7.
So this one is also the absolute minimum. Sometimes you won't have an absolute minimum, but that one is. Then we have one local, ladies, please, over there, you're supposed to be paying attention to this and writing, not disrupting class. Oops, I don't want to know. This one is a local maximum, and that is approximately 1/5 maybe, and -5. Now, I'm just approximating. There is no absolute maximum on this one. Why is there no absolute maximum? Going up forever. It's approaching infinity, positive infinity forever. So there is no absolute maximum. All right, so any questions about that? Okay, I'm going to give you a choice here. Either we can get the Chromebooks and you can take your quiz now, and we'll finish our other notes after lunch, or we can finish taking notes now and you can just get your Chromebooks on your way back in from lunch and do the quiz after lunch.
Finish notes.
Finish the notes. I think it'll be less disruptive than having to get over there if we finish our notes.
I believe so.
Okay, so the other packet that you picked up for notes today says even and odd. It was a long time ago. Okay. The bottom line when you're looking at the graph is y-axis symmetry is an even function. So y-axis symmetry is even. Origin symmetry is odd. Now let me distinguish between an odd degree and an odd function. That does not look good. Generally speaking, an odd function will be an odd degree, but not every odd degree function is an odd function. And I know that nomenclature is confusing, but to be an even function, it has to be symmetrical across the y-axis. If I take this parabola and I move it, say I move it over here, right? If I took that parabola and I moved it over here, it's still an even degree. It's still a quadratic. It is no longer an even function because it is not symmetrical across the y-axis. Does that clear? Does that make sense? Same thing is true for the odd function. If I move it somewhere else so that it isn't around the origin, so if I moved this up here, it is no longer an odd function, but it is still an odd degree. It's still cubic. 3 is still an odd number, but it's no longer an odd function. Right? So the way this works, let me switch back to my pen. If f of x, if the point xy is on the graph, so if I pick this point right here, which is 2, 0. If that point is on my graph and this graph is even, it's symmetrical across the y-axis, then the point -2, 0 must be on the graph. That's a parenthesis, not a bracket. So if xy is on the graph, then -x, y has to be on the graph. If both of those, if that's true for every x and y, then the graph is symmetrical across the y-axis. So a function whose graph has y-axis symmetry is an even function. And just keep reminding you, FN is abbreviation for function. All right. So the way it works with origin symmetry is that you need to be able to rotate this around the origin and it matches back up with itself without going 360 degrees. Obviously, if you spin it all the way around, every graph will end up matching. But we need a point on this graph to match a point on this graph just by rotating it around. So the easy way to think about that is if this point, let's pick one. That looks like 1, 2, 4, 6, 8. So if 8, 2 is on the graph, then -8, -2 has to be on the graph. So if xy is on the graph, then -x, -y is also on the graph. So a function whose graph has origin symmetry is an odd function. Anybody not finished with that in your notes? Okay, so I need to move this up a little bit. Now, when you look at this next graph, what's the first thing that comes to mind about this graph?
Parabola.
It's a parabola, but that's done what? Flipped. It's reflected across the line y equals x, right? Is this a function? Is this graph a function? Do you remember what that means? Do you remember the vertical line test? Does this function pass the vertical line test? No. So this is not a function. Right? It does not pass the vertical line test.
What is the vertical line test?
The vertical line test is when you draw a vertical line anywhere on the graph. That vertical line does not cross the graph in two places at the same time. If it does cross the graph in two places at the same time, the graph is not a function. So, for example, if I draw a vertical line right here, I can see that it's crossing in two places. Right? It crosses the graph in two places. Therefore, this graph is not a function. But if we look at x-axis symmetry, if xy is on the graph, then x negative y is also on the graph. And a graph with x-axis symmetry is not a function. So we have two tests that we do algebraically. If we have a graph, you can just look at it. Visually look at it. If it folds on the y-axis, if it's a reflection across the y-axis, it's an even function. If you can rotate it around the origin, it's an odd function. But if you don't have a graph, and you're expected to be able to tell a function from its equation, then we have two methods for testing if a function is even or odd. If it's even, f of x is equal to f of negative x. So basically what that means is we're going to solve it algebraically with an x, but what that means is that f of 2 would equal f of negative 2, right? That means that those would be equal. If it's odd, f of negative x is equal to negative f of x. So this would be like saying f of negative 3 is equal to negative f of 3. So if we put in f of 3 and we got a value and then we negated it, we should get the same answer as if we just plugged in negative 3. So that's the difference in the two statements. Everybody have this part? The next part on your, almost, let me wait. The next part on the next page has you filling in a table and looking at it. I want to give you the notes for the algebraic. I'm going to leave the filling in the table part to you. I think you can fill in a table. I mean, this is pre-cal. You should be able to fill in a table. All right, everybody finished with this one? So we're going to look at algebraically. You know what? I don't want to. I'm going to give myself a little more room to work. Yeah. We have 15 minutes until we go to lunch, and we'll finish with these notes before lunch, and then you'll be able to do the quiz when you come back. So, check to see if it's even, odd, or neither. If I don't have a clue, well, I kind of do have a clue on this one because it's an odd degree. It isn't going to be even. If you don't have a clue, I always check for even first because half of what you have to calculate with even, you have to do it for the odd either way. But since I'm looking at this and I know this is an odd degree, then I'm going to start with odd. All right, so we want to know if f of negative x is equal to negative f of x. That's our test to see if it's odd. So the way we do that is we put in a negative x where the x is. So f of negative x is negative x cubed minus 4. What happens to a negative when you raise it to an odd degree? So you multiply a negative times itself 3 times. It's still negative because it's 3 times. So this is still negative x cubed minus 4. Right. Now we need to check what is negative f of x. So in this case, we put the negative out front. We write the entire function inside the parentheses. And then we distribute this minus sign. So we have to distribute this to both places. So this gives me negative x cubed plus 4. Now here's our test. Does this one equal this one? No, it does not. So it is not odd. All right. I know it's cubic, so I know it isn't even, but we're going to test it anyway. The test for even says that f of negative x, which is here, has to equal our original function f of x. So we want to know, is f of x equal to f of negative x? So do these two equal each other here?
No.
No. So it's not odd. I mean, not even, sorry. It's not even. When it's neither even nor odd, we call it neither. Neither. So the correct answer to this, if I gave you this question on your quiz next class or on your test next week, and I said, is this function even, odd, or neither? The correct answer is neither, because f of x isn't equal to f of negative x, and f of negative x is not equal to negative f of x. Those two statements that were on the other side. This one's neither. Okay. I'm going to leave problem 3 for you to deal with. I want to look at problem 4. Okay. So we're going to check. We're going to do f of negative x first. If f of x is equal to f of negative x, it's even and we're done. But what happens here is the minus sign is still there. The x gets replaced with negative x. Then it's cubed. But this other x also has to get replaced with negative x. So every single x has to get replaced with negative x. Some of you are looking at me like you don't know what I'm talking about.
Why would it be negative x?
Because we're trying to find out what f of negative x is.
Okay.
So the function evaluated at negative x. So everywhere there's an x, we have to plug in a negative x. Okay? So we've already established negative x to an odd degree is still negative. So this is still negative. The x, negative x cubed becomes negative x. And then plus a negative x is just minus x. But this minus times this minus is now plus. So now we have a plus x here, minus an x there, which is 0. That is in no way the same as the original function, right? So this is not equal to f of x, or not equal to negative x cubed plus x. Therefore, it's not even. Okay? Are you getting this? Or do you have questions? Okay. Do you understand that we're substituting in a negative x wherever the x goes?
How do you know when to substitute the negative x? Is it for all of them?
We have to do both of those tests. On the other side of the paper, where we said if it's even, f of x is equal to f of negative x. So we plug in the negative x and see if they're the same, if they're equal. If they're equal, it's even. If they're not, then we have to check if f of negative x, which we've just calculated, if that's equal to negative f of x. It doesn't make sense when I'm saying it, because it all sounds the same. Okay, so this is the first test. Right? We plugged in the negative x everywhere there was an x. That's our first test. The next test says if f of negative x is equal to negative f of x, right? This is our second test that was on the front of your paper. But we've already calculated f of negative x, and we know that's equal to 0. Right? We did f of negative x right here, so I'll just write it over here. F of negative x is equal to 0.
Okay.
So now we have to see if that's equal to negative f of x. So negative f of x means we put a minus sign in front. We put f of x inside the parentheses, which is negative x cubed plus x. So this is our original function right here. This is our original function. We put a minus sign in the front. So now we distribute this minus sign. So negative times a negative is positive x cubed. And negative times that positive is minus x cubed. Does this Does this function equal, does
It won't be X.
this function equal 0? No.
It won't be X cubed.
Oh, it won't be x cubed. Thank you. Hang on. Let me fix that. Who told me that? What's your name? You get extra credit when you find a mistake. Gives you some incentive to pay attention. So f of negative x was equal to 0. So here's our test. Right here. Our test said, is f of negative x, which was equal to 0, is that equal to negative f of x, which is equal to x cubed minus x? Are those equal? No. So therefore, it's not odd. So so this one is also neither. So the answer to this one is neither. All right. You have 6 minutes before we go to lunch. I want you to practice by doing problem 3. So you're going to do the two tests that were on the other side of your paper at the bottom, right? For the f of negative x, you put it inside. For the negative f of x, you put it outside. Okay, so you're doing problem 3. You're using these two tests to determine if it's even, odd, or neither. Yes.
And it goes inside.
Yes, it goes inside. So is the absolute value of negative x is just x, right? And the absolute value of x is just x when it's positive, when x is positive. So f of x, you don't add any decimal places. When x is positive, so f of negative x is equal to f of x, which is positive. I mean, we're assuming from this discussion. Otherwise, it's just equal. So those are equal. Therefore, it's equal. And you're done.
Now I distribute the negative outside.
No, you don't have, you're done because it's even. If it was not even, if that had not been, right, then you would have to go into the other.
Okay, thank you.
If you think about it, I mean, it's an absolute value function that has to be right there at the origin. It's going to be even no matter what.
Okay, so the negative inside.
Replace that x with a negative. So what you want to write down f?
I'm really bad at it.
Negative x.
You have a negative x. So there'll be a positive. Set it down.
Set the value down.
If it was on, you're further into it. It's absolutely out.
If I have,
When you make a negative, it's even no matter
absolute
what.
value,
When you make a negative,
if I take negative, I would have
if it's absolute value, you don't know origin. What it is, so you can't move that around.
So this would be an absolute value, goes away with the negative, on this comes up a positive value. So if I have positive value,
What do you mean the better?
right? So they are,
Yeah, because your equation.
Think about your the average height and we have a left and right.
Okay, so the second test guy.
You know it's symmetrical across the y-axis. You know from the graph, but it's even by the calculation. The result of this, even if this had been a negative 2, that was almost water.
Really? They're too big?
I've never worked like I feel average, right?
Wait, you didn't get that?
When you talk,
You've actually got a speech really well.